Hello everybody, and welcome to the continuation of exercise 6. In this video, we're going to be looking at parts D and E of this exercise, and let's remind ourselves of the situation. So we're given the graph of a function little f, and we're defining a new function capital F to be the integral from 0 to x of little f. Okay, and a key observation that we made in parts A through C was that this graph that we're given is really the derivative of capital F. We're going to use that throughout. Okay, so let's get started thinking about part D here then. It's asking us where capital F of x is a concave down function. Okay, well the first thing we might remember is that a function is concave down when its second derivative is negative. So that would happen where the second derivative is negative, but the problem is we don't have a graph of the second derivative. Okay, so how do we answer this question? All we have is a graph of the first derivative of capital F. Okay, well here's where it's helpful to remember that the second derivative of a function is negative where its first derivative is decreasing. Okay, so we can answer this question by looking at the graph of capital F prime of x, which we do have, and asking where is it a decreasing function? All right, well, let's see. I see a couple of intervals where that happens. So from here to here, our capital F prime is going down, and then again from here to there. Okay, from about 2 to 4. So it looks like we've got two intervals where this would happen, and so our answer is going to be let's see, the first interval looks to be about -3 to 0. Okay, and the second one, as we said, is 2 to 4. Okay, there's our answer to part D. Okay, what about part E? Okay, well, this is kind of a challenging problem. It's going to require us to really think carefully about the relationship between capital F and little f to answer all of these questions. So it's giving us a big list of numbers that we'd like to either estimate or calculate. Okay, so we'll take them one at a time, starting with f of 3. Okay, how do we do that? Okay, well remember how capital F is defined. It was an integral. So to calculate f of 3, we need to substitute in 3 for our x and calculate the integral of little f of t from 0 to 3. How do you estimate an integral? Well, remember that integral is about area, and so we need to go up to our function and find a way to estimate the area under this curve between 0 and 3. Okay, so we're kind of interested in the area under that little stretch of our graph. Okay, well, that's not a regular shape, so our best hope here, or our only hope, is to estimate it somehow. Okay, one way we can do that is just by using rectangles. So I'm going to choose to chop that interval from 0 to 3 up into 3 equal pieces and to use a middle sum. Okay, and this picture is a little bit small, so I'm going to do my best to draw this. Okay, if we draw in middle sum rectangles, remember we're using as the height of our rectangles the places where the curve hits the middle point of an interval. Okay, so we can add up the area of those 3 rectangles that I just drew in. That's going to give us an estimate, not an exact value, but an estimate of the area under the curve. Okay, so when you look at those 3 rectangles, what's the width of each rectangle? Okay, each rectangle has width 1, and so we just need to take the heights times the widths. All right, so if we start with the first rectangle, we need to estimate its height. It's a little hard to do on this scale, but I would estimate its height to be about 0.3. Multiply it by its width of 1. Then we'd move on to the second rectangle. What would you say the height of that second one is? Okay, maybe 1.7-ish. Okay, multiplied by its width. And then finally the third one, that has a height of, well, maybe a wee bit less than 1.7, but I'm going to round it to 1.7 as well. Okay, and so if we add up those 3 numbers, that should give us an estimate of this integral, which is going to give us an estimate of capital F of 3. Okay, that turns out to be 3.7 if you do the arithmetic there. Okay, so we have calculated a value for capital F of 3, and we're ready to move on to capital F prime of 3. Let's clear the board a little bit, get rid of some of these markings that we made. Okay, how would we calculate capital F prime of 3? Okay, well there, it's helpful to remember the relationship that we discovered in parts A through C. Capital F prime is the same as little f. So we can calculate capital F prime of 3 by just finding f of 3. That's just a y value of our function. Okay, so if we go to the graph, notice that at 3, it crosses through the x-axis, and so the y value there is just 0. Okay, so that's the value of capital F prime of 3. Okay, and moving on, next thing we want to calculate is capital F double prime of 3. But doing that calculation is like taking this equation above and just taking the derivative of both sides. So capital F double prime of 3 should be little f prime of 3. Then we have to ask ourselves, how would we get a number for something like that? Okay, well, remember what the interpretation of a derivative is. Little f prime of 3 in words would be the slope of the graph, the slope of the tangent line of f at x equals 3. So we're looking for a tangent line slope here. We need to estimate that as best as we can. All right, so let's scroll back up to our picture here for a minute. Okay, I'm going to get rid of the markings that we don't need anymore. And we want to do our best to draw in a tangent line to the graph of little f at x equals 3. Okay, and you know that this is not the easiest thing to do. I'm going to do my best to freehand this. Okay, so there's a tangent line, and we're interested in estimating that slope as best as we can. Okay, so I'm going to try to pick out two nice points here. So on this side, we've got a point that, what does that look like? About 2.5, 2.5. Okay, and then down here we've got a point that looks like 3.5 minus 2. We're just going to use rise over run to try to estimate the slope of that segment. Okay, so that's going to be approximately... Okay, let's peek at those points again. So negative 2 minus 2.5, that's the rise. Okay, and then over the run, 3.5 minus 2.5, that's just going to be a 1 in the denominator. Do that calculation, and we're going to get negative 4.5. Okay, so there's our estimate of capital F double prime of 3. We did it again by just estimating the slope of a tangent line to the graph of little f. Okay, and finally, we come to the last part of this. Would like us to calculate the integral from 2 to 4 of little f prime, and I emphasize that, notice that there's a derivative on that. It's not little f, it's little f prime that we want to find the integral of. Okay, and there's kind of a sneaky way to do this. Remember that we have the fundamental theorem of calculus, which says we can do an integral like this by finding an antiderivative of the function that we're integrating. But what would an antiderivative of little f prime be? Well, it would be just little f. Okay, and we'd need to evaluate that antiderivative between 4 and 2. And so we can do this calculation by just substituting in 4 and 2. So we really just need to subtract two y values here. Okay, so let's go back to our function and see if we can estimate those two numbers, f of 4 and f of 2. Okay, and again, let's get rid of the markings that we don't need anymore. Okay, f of 4 is sitting down here, and let's see, what do you think? The y value looks to be about negative 1.5 there. And f of 2, that's up pretty close to 2. We could maybe call it 1.8, that number. Okay, we just need to substitute those in and subtract the 2. All right, so we're going to get negative 1.5 minus 1.8, and that gives us Okay, that's an approximation, negative 3.3. Okay, and that number would be the value of this integral, and we have finished the problem.